journal and saying these are the model findings, right? So I think what you're saying is there any problem about delivering those sort of graphs from the model, maybe separately from the regular interface, or with the interface we've been looking at? Is there any problem with having a model that just has graphs as output?
Yeah.
Yeah.
So if you put in main the time plots,
Mm-hmm.
so that when you run the model, you see the time plots.
Right.
And instead of
Yep. Instead of all the things with glitch keys, kind of people running around or whatever. Yeah, there's no problem with that. But there's an even better solution, to be honest, which is, we haven't talked about this, but we'll be getting to it in the fullness of the next 2 days. And that is, each experiment can actually define its own way of displaying the results of the model, okay? And some experiments you might want to go to your default exploratory screen, but some experiments might just summarize the model results in a nice little graph without showing the visualization behind it. And in fact, those experiments will tend to run faster, because actually it takes a fair bit of mechanism to kind of keep those things zipping around and so on. And that's, believe me, it's not just eye candy. It's really important for us as maulers to sort of have a bird's eye view of what's going on. But when we want to present it with gravity and seriousness and at a high level, you can easily have experiments which will run much faster, typically, or considerably faster, certainly. And those can show graphs. They can show graphs that summarize over many runs of the model, typically. And those can be done in any logic. But I will repeat what I said to the question earlier, which is to wit that often we seek recourse for our more sophisticated or more polished depictions. We actually use external statistics packages, or graph. They don't have to be statistics, but we often do statistics, so we can establish confidence levels in the results that this intervention has a statistically significant difference from the baseline or what have you. And you'll find in some of our publications we've done exactly that with non-parametric statistical tests. But we'll also use those for the plots. And I personally like R a lot because I think it's got a huge variety of really rich graphing, but other people may prefer other charting platforms. But in any case, the answer is basically, yeah, you can run it in any logic with just displaying graphs in the same project that, 5 minutes later you can be running it and see the interface. It doesn't mean excising the interface from your model and forever, foregoing that option. Quite the opposite. It's just something that varies on a per experiment basis. Is that helpful?
Yeah.
Yeah. Okay. Good question. Other questions? This is just wonderful stuff. The questions I'm getting. So thank you. Yeah, Roberto.
Let's say, give you an example. I have a number of data sets.
Yeah.
That I use to develop some parameters.
Mm-hmm.
So that's the data that I already have.
Right.
And I want to create some scenarios in the future.
Yeah.
So what I do is I take the data from these data sets.
Yeah.
And use that to create the parameters. Then I go to the model and I put these parameters in.
Sure.
For example, the transition of diabetes, for example.
Sure.
And I estimate the transition from one to the other. The rates are different.
Yep.
In different subpopulations.
Yep.
So after that, but I don't have the data from a specific population.
Okay.
So I'm going to hypothesize, is that correct? To assume that population will have a different rates. So I run the model, establish a new parameter, and then I feed back that back to the original data set. Is that possible, or does it make sense? Or the question is basically, I have a data set.
Yeah.
I use that to create some parameters.
Yeah.
Then I run the model, create some new information, and I use that to to adjust or modify my data?
You can do that. I mean, you have to be cautious because if your model is systematically off, it may cause you to kind of increasingly have data that's consistent with it, but diverges from things in the world, and so you'd have to be cautious. I will say that broadly speaking, there's two basic uses of data, and I know I've spoke with some people here. There's two key uses. When you have data from the external world, it often interfaces in models in one of two key ways. Okay. One way is you use it to identify parameter values for the model. It could be anything from who's connected with who at what time to what's the average chance per year someone will update cigarette use from this background to what's the mortality rate for this demographic category, right? Okay. We do lots of stuff with that. So you put these things in a parameter, and that's great. And sometimes you get data from meta-analyses, sometimes you get it from literature reviews, sometimes you get it from primary data, sometimes you can get those things from large-scale survey instruments or what have you. Okay? So that's good. But there's another sort of data that's often much more voluminous. And this source of data doesn't relate to any one parameter. You can't take it and say, we're going to use this data to estimate this parameter. Why? Why can't you do that? Because it's from the real world in a way that's where all the effects of these different factors you're interested in understanding, the effects of mortality, the effects of natural history of disease, the effects of behavioral transmission of norms, the effects associated with birth rates and so on. They're all tangled together. It's messy data. It's data about the world concerning observed patterns that don't boil down to any one parameter in your model. This is typically most of the data. We have data on the number of incident cases of diabetes, over time, and that's not something we could say assume this to the model. That's a thing generated by the model. It's something that it's an emergent feature of the situation. It's not something that is an assumption in the model. It's an emergent feature of the situation, and hence in the model, it's an emergent feature of the model. How many people have diabetes? So we can't just say assume it. What we do there is, ladies and gentlemen, we calibrate the model to this data. We expect it to accord with this data. We expect it to be consistent with the data. We expect it to plausibly match the data or be similar to the data in terms of what it detects. Now, I'm speaking glibly because the exact criteria you use, you may be interested in capturing the trend, but not the specific numbers, for example. It's very common if you're working in an area where you're just, you have sort of rough information. Or you may be interested in capturing numbers, but you're not so worried about noise in the data, sort of variability and so on. And there's ways to deal with all this, but the big picture is we can make use of data by putting it into the model. We can make use of data to keep our model honest by comparing model results to that data. And there's a whole sub-area of modeling associated with that. And there are very sophisticated techniques of calibration and techniques that we also practice based on computational statistics, Markov chain Monte Carlo methods and sequential Monte Carlo methods, particle filtering. And these are very sophisticated techniques to kind of take this data and use it to the greatest effect, because it's about using the latest evidence and keeping the model, making sure the model's consistent with that evidence. Okay? So I hope that's useful. Yeah. But we can talk more about the specifics